So we got inducted into a little bit of ellipse and related stuff, tangents, etc. A point where I realized we will have to take a little bit of a detour, give you a quick crasher on complex numbers. The objective is not to teach you complex numbers, but give you at least that bit of complex numbers which would be required towards furthering our interest in ellipse. Now, first of all, few things which you perhaps already understand. The whole business of complex numbers started with solving this equation. They encountered this equation, they said we have to solve this equation. Now, if x was a real number, they couldn't find a real number x that would give us a solution to this equation. So they said, all right, we would refer to this number x equal to square root of minus 1 as I or iota. And then they said, so this I is an imaginary number whose square is minus 1. I square is minus 1. Now, combination of these numbers I with other real numbers led to numbers of the form x plus iy, x plus iy, and this was referred to as a complex number z, where x and y were conventional real numbers known to us. This is a complex number z, and essentially, in order to represent these complex numbers z, they said, let's look at a plane, the argand plane, in which a complex number z could be represented as an ordered pair x comma y. If there was a point in the argand plane, x comma y, then it was meant to represent the complex number z, right? So the argand plane designed specifically to represent the entire bunch of complex numbers of the form x plus iy, x and y are real numbers, where if there was a point P whose coordinates were x comma y, then this point P was a geometric representation of z. It was a point representation of the complex number z. So every complex number x plus iy, where x and y are real numbers, have a one-to-one correspondence in the argand plane. For every P in the argand plane, there is a unique complex number z. For every complex number z, there is a unique point P in the argand plane. Yeah, this plane is referred to as an argand plane. Yeah, but this time this point P would mean to us, as is understood between you and me, let's say we decide to call the number z as one being represented by the point P, x plus iy, right? So for every z there was a unique P, for every P there was a unique z. Hop in, quick. The way to locate a complex number z, that means a point that represented a complex number z, was one, of course, an ordered pair x comma y. You move x units parallel to the x axis, y units parallel to the y axis, and locate the point P, right? The other way the complex number z represented by the point P could be obtained would be in the form of two things. How far P is from the origin, that means R. In order to locate P, which is the complex number z, one of the things that you would require is how far it's from the origin, R, right? And this R is called mod z. How far P is from the origin is referred to as mod z. So R, the distance of P from the origin, is represented, is called modulus of z, mod z, and is given by very clearly root x square plus y square, is given by root x square plus y squared. Yes or no? But r is not enough, because given r, then what you get is a set of complex numbers lying on a circle centered at the origin and of radius r, right? So this is not unique. Therefore you would need, let's say, an angle theta. So a combination of r and theta would uniquely locate P. While this r is referred to as the modulus of the complex number z, this theta is referred to as the argument of the complex number z. This theta is referred to as the argument of the complex number z. Argument of z, or arg z, arg z. Now, for a given P, its modulus, that means its distance from the origin, is unique. But as far as theta is concerned, for a given R, several thetas could give you the same P and therefore the same complex number C, right? For example, theta equal to theta, theta equal to theta plus 2 pi, theta equal to theta minus 2 pi, theta plus 4 pi, theta minus 4 pi, and so on and so forth. Do you realize that? It's not just theta, but theta equal to theta plus 2k pi, where k is an integer, would locate the point P. Therefore, the argument of the complex number z is not unique. Is not unique. It's a multiple valued function. The argument, therefore, is a multiple valued function, right? Any one of these, when chosen as the argument with a given r, will locate the same point P. Yes or no? Therefore, the argument is not unique. The argument is a multiple valued function. And then they said, all right, you know, these are several values of theta that will give me the same P. What we do is, to be on the same page and to be talking of the same thing, let's choose to call of these values theta plus 2k pi, there would be only one number, only one value that will lie in the interval minus pi to pi. There would be, of all the thetas, there would be one theta, of all the thetas that you can choose to locate P, there would be one theta that would lie in the interval minus pi to pi. There would be one theta that would lie in the interval minus pi to pi. And that value of theta, all these are arguments, but of these arguments, of these several, very many arguments, one argument that lies in the interval minus pi to pi would bring us on the same page, and this value of the argument would be referred to as the principal value of the argument. It would be referred to as the principal value of the argument. Now, so arg z will have multiple values, of which one lying in the interval minus pi to pi would be referred to as the principal value of the argument. Yeah, this interval will bring uniqueness to argument. It's not just a convention, but a convention with a rationale, because this would be a unique value of theta that could be sought after, right? Sorry? Now, I'll come to that. Why we will not use 0 to 2 pi, I'll come to that also. It covers all possible locations. Minus pi to pi, it covers all possible orientations of this rotating line OP. Right? So you don't want to restrict. The P could lie anywhere, isn't it? Two rules of the game. The subject of chemistry I abhor. Starting from C to Y. add another a to it if you like. It'll bring value to the subject and will take away value from me. So any reference made to chemistry while we are discussing authentic maths and physics would be looked upon as blasphemous. All right? Absolutely sinful. So don't take recourse to chemistry while we are doing all this. Right? For some reason, I get shivers down my spine. Oh, so what's in a name? I don't know the name of the community that sets this. There is a mathematical society, International Mathematical Society. I don't exactly know the name of that society, but it's that society which sets these conventions. And unlike, see, as far as IUPAC is concerned, you know, you talk of IUPAC all the time in chemistry. In maths, they don't talk of the society, they talk of the concept. That's another difference. Okay. Consequently, we don't bother about which society, damn it. Okay. Now, forget all of that right now. All right, let's not divulge too much into unrelated domains. Let's focus on some very basic things so that we can jump into ellipse in a circular manner. So then, you know, suppose there is a point P here. Say this angle is 3 pi by 4. This represents a certain complex number, right? So one of the values of the argument is 3 pi by 4. Another value of the argument can be 2 pi plus 3 pi by 4. And do you realize that this angle is 5 pi by 4 in magnitude, but because it's clockwise, it's minus 5 pi by 4. So this is also an argument. And minus 5 pi by 4 plus 2 pi will also be an argument. These are all permissible values of the argument, but it's this value 3 pi by 4 that lies in the interval minus pi to pi, which will bring us to the principal value of the argument. All right. Suppose there is a point P in the Argand plane which represents a certain complex number, and say this angle is 5 pi by 4. Yes, one of the values of the argument of this is 5 pi by 4, but 5 pi by 4 does not belong to the interval minus pi to pi. Therefore, even though it's an argument, this is not a principal value. In fact, if you look at this value, this is minus 3 pi by 4, which lies in the interval minus pi to pi and would be looked upon as the principal value of the argument. Right? So any argument could eventually be reduced to its principal value. No matter what's given to you, it would crystallize to a principal value. Okay. Again, like I said, I can go on and on for this, but my intention is let me be very focused about what I want to communicate. Just a few more remarks. This x is written as REZ, means the real part of z. Real part of z. This y is written as the imaginary part of z. Which is IMZ. Which one that does not contain I? That's the real part of Z. Why? Because it's married to I, it's called the imaginary part of Z. Okay? Now, if y is 0, then Z is said to be purely real. Z is said to be purely real. If x is 0, Z is said to be purely imaginary. Z is said to be purely imaginary, right? Now, so the location of the complex number Z, x comma y, right? The ordered pair x comma y, the point P x comma y represents the complex number x plus iy, right? Now, in addition to complex numbers that not lie on the x and the y axis, right? Which means they will have real and imaginary part of complex number lying here will not have real part 0, imaginary part 0. Or here it will not have real and imaginary part 0, and so on and so forth. But if there are complex numbers that say lie on the x-axis, real axis, they will have imaginary part 0, right? If there is a z that lies here, then imaginary part of this z will be 0. Y will be 0, right? Now, if a z lies on the positive x-axis, then its argument is going to be 0. Argument of this z is going to be 0, isn't it? From O to P, the angle made with the x-axis is going to be 0, right? If there is a z that lies on the negative x-axis, again imaginary part of z is going to be 0, but argument is going to be pi. Argument of this z is going to be pi. So for a positive real number, argument is 0. For a negative, this is a negative real number essentially, right? This z is a negative real number. Its argument is pi. So in general, when the argument of z is 0 or pi, we can conclude that z must be purely real. We can conclude that z must be purely real. Yes or no? I mean, that's the same. I mean, I can add pi to this, this will become, I can add 2 pi to this, 4 pi to this. So there are multiple values. So if I'm talking of one value of the argument, then, you know, we are not interested in unnecessarily narrating and relating to other values of the argument, because we have uniquely located the point P with the help of the argument, which was the sole objective of that argument, right? So we will not get into that argument. Now, early for next class though, but very well welcome. If there is a complex number z lying on the y-axis, then its real part is 0. This z is, real part of z is 0, and this z is purely imaginary. If there is a z lying here, its argument is going to be pi by 2. Argument of the z is going to be pi by 2. If there is a z that lies here, again, it's purely imaginary. It's purely imaginary. Imaginary. Its real part is 0. And argument of this z is going to be minus pi by 2. So if z is purely imaginary, means 2i, 3i, 6i, minus 5i, minus 4i, minus 3 by 2i, right? If z is purely imaginary, then its argument will either be plus pi by 2 or minus pi by 2, right? So if argument of z, and conversely, if argument z is plus minus pi by 2, then z is going to be purely imaginary. Right? No. Positive and negative are only for real numbers. There is nothing like a positive. I mean, you can say imaginary number with positive real part or a negative real part, but also, see, suppose there is a complex number z1 represented by the point x1 comma y1. That means this complex number z1 would be x1 plus iy1. And another complex number z2, which is say x2 plus iy2, represented by a point x2 comma y2, an ordered pair x2 comma y2 and x1 comma y1 representing these two complex numbers. Now, the moment someone says z1 equal to z2, it really means that z1 and z2 are represented by the same point. Now, if they are represented by the same point, they will have the same x coordinate and the same y coordinate, yes or no? Yes, right? z1 equal to z2 means the same point represents the two complex numbers, and therefore their x and y coordinates must be the same. So this would obviously mean x1 equal to x2 and y1 equal to y2. That means if two complex numbers are equal, their real parts and their imaginary parts could be equated. Their real part and imaginary part could be equated, right? Say, for example, if I have 2 plus t times I is x plus 3i, then I can say x must be 2 and t must be 3. X must be 2 and t must be 3. Clear? Tan inverse y by x, one of the values of the argument. But with the same argument you can have multiple complex numbers, isn't it? Say there is a point P here. This represents a complex number ZP. There is a point Q here. This represents a complex number ZQ. Both have the same argument. So if the argument is the same, doesn't mean that the two complex numbers are the same. For two complex numbers to be the same, not only should their arguments be the same, but so should their mod. See? P and Q are two complex numbers having the same argument, but are they equal? No, the modulus of P is this, the modulus of Q is this. They are different complex numbers, right? That's why. Also, see, Z1 equal to Z2, again in an algebraic sense, x1 plus iy1 is x2 plus iy2, right? This could have been written as x1 minus x2 is I into y2 minus y1, yes or no? Now if I square both sides, x1 minus x2 whole squared is I square is minus 1. So that's minus y2 minus y1 whole squared, yes or no? Where x1, x2, y1, y2 are all real numbers, they are all real numbers, and therefore their squares cannot be negative. Square of a real number cannot be negative. See, x1 minus x2 will be real, so its square will be non-negative. y2 minus y1 is real, so its square cannot be negative. And this gives me x1 minus x2 whole squared plus y2 minus y1 whole squared is 0. Now these are two non-negative numbers and they add up to 0. When can two non-negative real numbers add up to 0? When each is 0. When each is 0. So this would mean this is 0, x1 equal to x2 therefore, and this 0 would mean y1 equal to y2. That's why if two complex numbers are equal, you can equate their real and imaginary parts. Also, if two complex numbers are equal, their modulus must be the same, their argument must be the same.
So why should the argument be the same if I add 2 pi?
No.
The principle has to be.
No, the point is, any one argument can be looked upon as a common argument to the two complex numbers. They are all the same. I mean, pi by 3 and 2 pi plus pi by 3 and 4, they are the same arguments. They are not looked upon as different arguments, isn't it? They are actually the same argument. Yes, absolutely. This is the distance between P and Q, which is 0. That means the same point, the 2 points coalesce into one, right? Now, suppose P represents a complex number Z. Z could be say x plus Iy. That means the coordinates of P are x comma y. Coordinates of P are x comma y. R is the modulus of Z and theta is the argument of Z, right? So the point x comma y represents the complex number Z, right? A reflection of P about the x-axis would be P prime, yes or no? The coordinates of P prime would be x comma minus y, right? And this represents a complex number x plus I times minus y. Isn't it? Isn't it? If P and P prime are mirror images of each other about the x-axis, if P and P prime are mirror images of each other about the x-axis, then the two complex numbers that they represent are said to be conjugates of each other, That means if this is Z, then this complex number which is represented by P prime is referred to as Z bar. The conjugate of Z. They are conjugates of each other. Z is the conjugate of Z bar and Z bar is the conjugate of Z. So if Z is x plus Iy, then its complex conjugate is given by Z bar, which is x minus Iy. That means, can you also see that their modulus for P and P prime, the modulus is the same. These two triangles are congruent, right? So if this is R, do you see that this is also R? And if this is theta, then this is minus theta. That means if the argument of Z is theta, then the argument of Z bar would be minus theta. If the argument of Z is theta, then argument of its conjugate is going to be minus theta. Yes or no? Yes, sir. One of the values of the argument. Not necessarily the principal value, but one of the values of the argument, right? X minus Iy, right? Also, so this is Z bar, a complex number x minus Iy. If I take the bar of this, that means all that I do is change the sign of the imaginary part. So that's x plus Iy, which is Z. So Z bar bar is Z. Z bar bar is Z and Z bar 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 would be Z bar. So right. So if you take an even number of bars, you get Z. If you take an odd number of bars, you get Z bar. Right? Isn't it? Not only that, Z bar is x plus Iy into x minus Iy. Right? Which is like x squared minus Iy whole squared. And I squared is minus square. Minus I squared is minus 1. So this becomes x squared plus y squared, which is actually mod z squared. So z bar would be mod z squared. Z bar is going to be mod z squared. Right? And like mod z has the same as mod of z bar, right? They have the same modulus, but argument z is minus argument z bar. Right? Now, if z is x plus Iy, z bar is going to be x minus Iy. Right? Z plus z bar is going to be 2x, which is twice real part of z, Right? X is the real part of z, which is the same as twice real part of z bar. right? Z minus Z bar divided by 2I is going to give me y. Z minus Z bar divided by 2I is going to give me y. Yes or no? Which is imaginary part of Z. Imaginary part of Z. Z plus Z bar by 2, Z plus Z bar by 2 will give me real part of Z. Z minus Z bar by 2I will give me imaginary part of Z. Right? Now, few things which I want you to know. Of course, we'll come to those things in greater details when we do calculus, but a quick mention. Cos theta, when theta is in radians, can be looked upon as an infinite series. Can be looked upon as an infinite series. When theta is in radians, is 1 minus theta squared by 2 factorial plus theta to power 4 by 4 factorial minus theta to power 6 by 6 factorial and so on and so forth. This is called the Taylor expansion of cos theta. Taylor expansion of cos theta, not T-A-I, T-A-Y. T-A-Y-L-O-R. Taylor's expansion of cos theta, infinite expansion. Not that the proof is beyond you, but it's only beyond you for the time being. While we are in the midst of class 12, I'll offer a formal proof for the same. When theta is in radians, cos theta. And do you realize that on replacing theta by minus theta, nothing changes? So that's the reason cos minus theta is the same as cos theta, right? Similarly, when theta is in radians, sin theta can be expanded as theta minus theta cube by 3 factorial plus theta to power 5 by 5 factorial minus theta to power 7 by 7 factorial and so on and so forth, signs alternating, and only odd powers of theta. Very clearly, if theta is replaced by minus theta, the sign of each of the terms will change, and therefore sin minus theta is the same as minus sin theta because of this expansion. And e power x, the expansion of e power x is 1 plus x square by 2 factorial plus x cube by 3 factorial and so on and so forth. That's the infinite expansion of e power x. E, as you know, is an irrational number. And now, having said this, can I wipe this off? Look, if there is a complex number z, which is represented by the point P, say the modulus of the complex number z is r. R is modulus of z, which is distance from the origin, root x square plus y squared. Theta is the argument of the complex number. Theta is the argument of z, right? Then this length, the x coordinate of P is going to be r cos theta. The y coordinate of P is going to be r sin theta. Right? Yes or no? Therefore, x for the point P, its x coordinate is r cos theta and its y coordinate is r sin theta, isn't it? So the complex number z is x plus iy, which is r cos theta plus I sin theta. Yes or no? X plus iy, which is r cos theta plus I sin theta. This is called the polar representation of the complex number z. This is the polar representation of the complex number z. Now, r is the modulus, theta is the argument, right? Now this cos theta I expand as 1 minus theta squared by 2 factorial plus theta to power 4 by 4 factorial and so on and so forth, even powers of theta, right? 1 minus theta squared by 2 factorial plus theta to power 4 by 4 factorial minus theta to power 6 by 6 factorial and so on and so forth, right? Plus I times sin theta, which is theta minus theta cube by 3 factorial plus theta to power 5 by 5 factorial. Yes or no? Now, let me collect terms and write purely in ascending powers of theta. Ascending powers of theta. So when I do that, then z r 1 plus I theta, right? And this minus 1 is I square, yes or no? So this could have been written as I theta whole squared by 2 factorial. Right? Then minus I, see, I cubed is actually I squared into I, which is minus I. So this minus I can be written as I cubed. So I theta whole cube by 3 factorial. Similarly, look at this, plus 1. Plus 1 is I to power 4. I square whole squared. I square whole squared is I to power 4. Yes or no? So I theta whole to power 4 by 4 factorial and so on and so forth. Let's see. 1 plus x square by 2 factorial plus x cube by 3 factorial x power 4 by 4 factorial etc. is going to be e power x, where in this case x is I theta. Yes or no? Right? Z therefore is r e power I theta, right? R is the modulus of the complex number, theta is the argument of the complex number, where cos theta plus I sin theta actually got reduced to e power I theta. Cos theta plus I sin theta got reduced to e power I theta. This representation of the complex number is called Euler's representation. Euler's representation. Where r is the modulus of the complex number, theta is its argument. Theta in radians. And from now on, if we talk of theta, we talk of theta in radians. If we talk of logarithm, we talk base e, right? So that's the default convention. So, if this point P is Z is R e power I theta, right? Which is R cos theta plus I sin theta. R is the modulus, theta is the argument. Then its conjugate P prime would have same modulus R, but its argument would be minus theta. So the Z that represents P prime, that is Z bar, which is going to be R is the same modulus, e power minus I theta is going to be e power minus I theta. Right? Hmm? One I could have been written as 0 plus 1 into I, yes or no? Right? Which is cos pi by 2 plus I sin pi by 2, yes or no? Sin pi by 2 is 1, cos pi by 2 is 0. Cos theta plus I sin theta, therefore e power I theta, e power I theta. So one of the values, one of the ways it could be written as e power I pi by 2. Right? Or in a more general sense, it could have been written as cos pi by 2 plus 2k pi plus I sin pi by 2 plus 2k pi, which is cos theta, which is e to power I pi by 2 plus 2k pi, where k can be any integer. No? Now, so one way I could have been written as this, right? So I is e power I pi by 2, right? I to the power I is e to power I pi by 2 whole to power I e to power minus pi by 2. Which is a real number. Complex to the power complex can be real. E power minus pi by 2 is a real number. Yes or no? E power minus pi by 2 is a real number. Right? Minus 1 is like minus 1 plus 0 into I, which is cos pi, one way is cos pi plus I sin pi, which is e power I pi, which is e power I pi. Cos theta plus I sin theta, e power I theta, e power I pi. To kill it, to a poor little fellow. Minus 1 is e power I pi. Clear? If Z is e power I, damn thing, get out. If Z is e power I theta, then what's the mods? What mod Z? Mod Z is 1 e power I theta. Z bar is going to be 1 e power minus I theta. Right? And do you realize Z plus Z bar? What is e power I theta? Cos theta plus I sin theta? Euler. Hope it's not you. I'm discussing you, man. Cos theta minus I sin theta. Right? Then z plus z bar is going to be 2 cos theta. Z plus z bar by 2 is going to be cos theta. Z plus z bar by 2 is going to be cos theta. And z minus z bar by 2i is going to be sin theta, where z is e power I theta. If z is chosen as e power I theta, then cos theta is z plus z bar by 2 and sin theta is going to be z minus z bar by 2i. Yes or no? Do you all understand this? Yes. Shall I take the liberty of going some more stages, although that will not be required in ellipse, but shall I go ahead and discuss those things now, if you are okay with it? Huh? Okay. I chose that e power I theta as some z. That was just out of my choice, right? I selected a z equal to e power I theta. So z bar would become e power minus I theta, which is cos theta minus I sin theta, right? So just in case, if z is this, then z bar would be this, and therefore it's going to be this. Right? Okay. See, if z is r e power I theta, whatever I'm going to tell you from now on in complex numbers is not related to what I would be using in ellipse, but since I've come to this point, might as well tell you a few more things, right? R is the modulus of the complex number z, and theta is the argument of the complex number z. Theta is the argument of the complex number z. Clear? Now, suppose there is one complex number z1 whose modulus is r1, whose argument is theta 1. There is another complex number z2 whose modulus is r2, whose argument is theta 2. Right? Now, the product of two complex numbers would be another complex number. If x1 plus iy1 is multiplied with x2 plus iy2, you would get something like a plus ib, which would be yet another complex number. Product of two complex numbers is also a complex number. So if I multiply these two complex numbers, I'll get yet another complex number, z1, z2. It's complex. Every real number is a complex number with imaginary part 0. From now on, all numbers that you have looked at are complex numbers. 1, 2, 3, 4 are complex numbers with imaginary part 0. That's the way we look at everything from now on. Okay? So let's migrate from the real world to the imaginary world. Okay, because the imaginary world is the real world. z1, z2 is yet another complex number, right? The z1, z2 is another complex number. If I multiply these two, then I end up getting r1, r2, e power I, theta 1 plus theta 2. Yes or no? Now, modulus of this is a complex number, and what is its modulus? r1, r2. This is a complex number, what is its argument? Theta 1 plus theta 2. So modulus of z1, z2 is r1, r2, yes or no? But what is r1? Mod z1. What is r2? Mod z2. This is one property. So mod z1, z2 would be mod z1 into mod z2, right? Now, argument of this complex number z1, z2. is theta 1 plus theta 2? Is theta 1 plus theta 2? But what is theta 1? Argument z1. What is theta 2? Argument z2. So it brings us to yet another property. Argument of the product would be sum of the arguments. Behaves like logarithm, isn't it? Behaves like log. This argument operator behaves like the log operator. Log AB is log A plus log B kind of a thing, right? Now, one thing, even though argument z1 may lie in the interval minus pi to pi, argument z2 may lie in the interval minus pi to pi, but their sum may not lie in the interval minus pi to pi. So even though both of these may belong to the principal valued interval, but their sum may not necessarily belong to the principal value. But this will still be looked upon as an argument, even though not the principal value of the argument, some argument. What's the big deal about it? Clear? Similarly, so mod z1 z2 is mod z1 into mod z2. Modulus of the product of two complex numbers would be product of their moduli. Argument of the product would be sum of the arguments, right? Similarly, z1 by z2, ratio of two complex numbers is yet another complex number. Ratio of two complex numbers is yet another complex number. This is r1 by r2 e power I theta 1 minus theta 2. Now, z1 by z2 is a complex number whose modulus is going to be r1 by r2. So, modulus of z1 by z2 is r1 by r2. But what is r1? Mod z1. What is r2? Mod z2. Right? Similarly, argument of z1 by z2 is what? Theta 1 minus theta 2. But what is theta 1? Argument z1. Right. Log A by B is log A minus log B. So, similar behavior. Argument z1 minus argument z2. Even though this may not necessarily be the principal value of the argument, but given any one of the values of the argument, you can reduce it to an interval that belongs to minus pi to pi suitably. Okay. Now, if z is r e power I theta, then z to power n is going to be r to power n e power I n theta. Yes or no? If z is a complex number, z to power n will also be a complex number. What is modulus of z power n? R to power n. But what is r? Mod z. So this is mod z whole to power n. That means mod of z to power n is mod z whole to power n. You know what I'm saying? So if someone says mod of, what is mod of 2 plus 3i whole to power 50? You can say that's the same as mod of 2 plus 3i whole to power 50. You can say this. So modulus and the power are interchangeable in an operation. Clear? So what is argument of z power n? N theta. N theta, which is n into argument of z. Log of a to power m is m log a. Similar kind of stuff, right? Even though this may not necessarily be the principal value of the argument. Now, shall I take a few more stages into complex numbers? You're okay with it? Huh? Come down to position vectors. come down to position vectors. See, a position vector R, which is x I cap plus y j cap. I cap and j cap are unit vectors along the x and the y direction. What is this goddamn position vector doing? All that it is doing is locating a point x comma y in the plane. Locating a point x comma y in the plane. Its I cap and j cap are entities that are non-arithmetical. They are vectors. They are non-arithmetical, but they are symbolic in character, suggesting that you move x units parallel to the x-axis, y units parallel to the y-axis to locate a point P, x comma y. The position vector of this point P is going to be xi cap plus yj cap is going to be the position vector of this point P. This is what it's doing, right? Now, in contrast to I cap and j cap are non-arithmetical. They are suggestive of what you have to be doing, right? The iota I square root of -1 is arithmetical in character. You have the luxury of performing all arithmetic operations with iota or I. Not with I cap and j cap, but I, which is square root of -1, all arithmetical operations can be performed. You can multiply, you can divide, you can raise it to a power, whatever you want. All arithmetic operations that you have learned, you can perform with I, but not with unit vectors I cap and j cap. However, look at this z in the Argand plane, x plus iy. What is this doing? This also is locating a point P with coordinates x comma y. Yes or no? X comma y. This is what this z does. This z is doing what this r did. This z is doing what that r did. Right? This also is saying that move x units parallel to the x-axis, y units parallel to the y-axis. xi cap and yj cap were independent operations, non-interfering. This operation x plus iy is also non-interfering. It's like moving x units along the x-axis, y units along the y-axis to locate the point P. What's the difference between R and Z then in terms of what they are performing? No difference. No difference. They're doing the same thing. They are actually doing the same thing. Right? And if they're doing the same thing, then in the Argand plane, I can call Z the position vector of the point P. I can refer to Z as the position vector of the point P. Yes or no? Right? Therefore, this vector OP henceforth would be referred to as Z, the position vector of the point P. Z then would be referred to as the position vector of the point P. Clear? This R had two properties, its length and its orientation. Right? Mod R, which is its length, and theta, which is a measure of its orientation. That's what this R had. The Z also has two properties. Its length, which is mod Z. This vector is Z. Henceforth, I'll call this vector Z. This is mod Z, and this is the orientation factor, which is called argument Z. In this case, tan theta would be y by x. In this case also, tan theta would be y by x. Do you understand? So can I not be conclusive about the fact that Z is a substitute for R? Z is a substitute for R? Yes or no? And अरे वो तो नाम दे रहे हैं हम उसको आर्गन, वो तो प्लेन ही है, इस प्लेन को आर्गन प्लेन बोल दो. Now Let that guy keep talking. Now, again, when you equated two position vectors, x1i plus y1j equal to x2i plus y2j cap, then you said x1 equal to x2, y1 equal to y2. The same thing you did with two position vectors, z1 and z2. If x1 plus I y1 is x2 plus I y2, then x1 is x2 and y1 is y2. So do you realize that they seem to be having common properties? Because both actually represent an ordered pair xy. Both are leading to a point. But their representation, their symbolic representation is slightly different. This involves an arithmetical operator I. This involves I cap and j cap. Those are notional. These are notional operators. Just telling you move x units along the x-axis, y units along the y-axis. You can't say what is I into I. You have defined operations like I dot I and I cross I, but there is nothing like I into I. I cap into I cap, I meant. There is nothing like j cap into j cap. There is nothing like I cap to the power I cap. But there is, I have demonstrated that there is I to power I. So this has a fresh dimension to it. Not only is it inheriting all properties of position vectors, in addition it has its own. Because it is capable of rendering all arithmetic operations. Yes or no? Yes. Are you all there with me on this? Right? Now, hello. Now, if this was a position vector R1 and this was a position vector R2, right? Then I could perform triangle law of operations on this, right? And that would give me, this would be a vector which would be R2 minus R1, final position minus initial position, triangle law vectors, right? This vector R1 locates a point P. If a vector has one end at the origin, it will locate a point P and therefore a position vector. But I could move this vector parallel to itself. I could move this vector parallel to itself, in which neither the orientation changes nor length changes. Then this vector is R1 but not position vector R1. For it to be deemed a position vector, its one end must be sitting at the origin so that it can locate a point P. So this vector is R1, this is also R1. But this is a point representation of the point P. This is a vector representation of R1, right? A vector can have a point representation leading you to a point if one end is at the origin. The other one is simply a vector. This is R1, this is R1. They are all R1s, right? So the same thing is inherited by complex numbers. See, if this point P is represented by the position vector z, z is x plus iy, moving x units parallel to the x-axis, y units parallel to the y-axis, right? This is the position vector z of the point P. This is the position vector z of the point P, right? This vector, position vector, locates a point P with coordinates x comma y. It has two properties, its modulus, which is this length, its orientation, which is its argument theta. Now, if this is a vector z, I could move it parallel to itself and it will still be z. It will still be z. It will still be z. This vector will also be referred to as z. The length of this vector would be root x squared plus y squared. The angle that it makes with a line parallel to the x-axis will still be theta, which is the orientation factor of z. Are you coming to terms with all of this? Yes or no? Huh? Now, aha. This is the vector z1, x1 plus iy1, right? This is the vector z2. Ah, wow. Then this vector from triangle law would be final position minus initial position, which is z2 minus z1. Right? This is a vector z2 minus z1. But is there a point in the Argand plane whose position vector is z2 minus z1? Yes, yes. What I do is I move this vector z2 minus z1 parallel to itself so that this sits here. Then this vector would be z2 minus z1. And then this point P is represented by z2 minus z1. Please ask. Got me? So this is just a vector z2 minus z1. This length would be mod of z2 minus z1. This length will also be mod of z2 minus z1. And this makes an angle theta with the positive direction of the x-axis. That will be the argument of z2 minus z1. That will give me the argument of z2 minus z1. This angle will give me the argument of z2 minus z1. Yes or no? Right? I can therefore see, if this was a vector r1 and this was a vector r2, then I could deploy parallelogram law of vectors. This vector would be r1 plus r2. If this was a certain vector z1, not necessarily the position vector, but some vector z1, and if this was some vector z2, on completing the parallelogram, this would be the vector z1 plus z2. This length would be mod of z1 plus z2. The angle that z1 plus z2 makes with a line parallel to the x-axis will give me argument of z1 plus z2. Yes or no? Are you all there with me on this? Huh? Got me, now? Also, this length is mod z1. Now, if this vector is z2, what is this vector? This is also z2 essentially, right? Now, can I say mod of z1 plus z2 is less than or equal to mod z1 plus mod z2? Can this be said? This length is mod of z1 plus z2. This is mod z1, this is mod z2. This side of a triangle cannot exceed the sum of the other two sides of the triangle. Yes or no? Yes, sir. Right? This is the triangle inequality in complex numbers. This is the triangle inequality in complex numbers. Triangle inequality in complex numbers. Clear? Yeah, I'm saying they can be equal. That's why I put equality also. Why? When did I ever say that or prove that? I said mod z1 z2 is mod z1 into mod z2, but I never told you mod z1 plus z2 is equal to mod z1 plus mod z2. I mean, if you are skeptical about this, take mod of 2 plus 3i plus 5 plus 4i. This is z1, this is z2, right? And mod z1 is 2 plus 3i and mod z2 is 5 plus 4i. Is this equal to this? This actually is mod of 7 plus 7i. Is this equal to this? No, in general not, isn't it? Now, are you all in sync with me or are you getting flooded? No? Then shall I teach you some more complex numbers? Huh? Okay. Nahi yaar, this is not even the beginning. You will now realize why I chose not to teach you complex numbers when you came in as toddlers. Still are, but let me give you some more ideas now that we've come to this point. Some more things. Okay? See, suppose this is a vector z. This is a vector z. This is r, this is theta. Z therefore is r e power I theta. This is a vector z, position vector of the point P. OP, the vector OP is the position vector z, right? R e power I theta. Suppose I take a point Q and say this angle is phi and this is r. Let's say this represents z prime. Say this represents z prime. This vector is z prime. This vector is z prime. Position vector of Q is z prime. Can I say z prime is r e power I phi? Now, say this angle is alpha. Phi minus theta is alpha, say. This is r e power I. Phi can be written as theta plus alpha, which is r e power I theta into e power I alpha. Yes or no? But r e power I theta is z. R e power I theta is z. This is z e power I alpha. Yes or no? This is z e power I alpha. Now, the important thing is the following. There was a vector z like this. And there was a vector z prime like this, and the angle between them was alpha. If this vector z was multiplied with e power I alpha, what did it do? It gave me z prime. That means it rotated the vector z by an angle alpha. What did e power I alpha do? It rotated z by an angle alpha because we got z prime. When I multiplied z with e power I alpha, I got z prime. That means z got rotated by an angle alpha, right? That means e power I alpha is an operator. E power I alpha is an operator which, when multiplied with a vector, it rotates the vector by an angle alpha. You know what I'm saying? E power I alpha therefore comes up as a very prominent, potent, powerful operator. If you take any vector and multiply it with e power I alpha, you can rotate the vector by an angle alpha. Did you have anything of this sort in vectors? No, you didn't have. You didn't have something as versatile as this in vectors. Now you have a wonderful operator. If you want to rotate a vector z by an angle 30 degrees, multiply it with e power I pi by 6. If you want to rotate it by, and this is 30 degrees anti-clockwise, but you want to rotate it 30 degrees clockwise, multiply it with e power minus I pi by 6. Right? You have handle over how much you want to rotate and the sense in which you want to rotate. Multiply it with e power I alpha. If alpha is positive, anti-clockwise rotation. If alpha is negative, then clockwise rotation of the vector takes place. Yes or no? Right? In fact, if this was a point P with position vector z0, if this was a point P with position vector z0, I hope it is not getting very burdensome and I'm not dumping it all too prematurely on you. I hope you are able to settle to these thoughts, right? There is a point with position vector z0, right? There is a point A with position vector z1 say. That means when joined to the origin, that vector would be A. When joined to the origin, that vector would be z0. So what would this vector be? This vector would be z1 minus z0, final position minus initial position. Yes or no? This is B say with position vector z2. Then what would this vector be? z2 minus z0. z2 minus z0. Yes or no? Yes. Now, suppose the angle between them is alpha. Suppose the angle between them is alpha. Between these two vectors is alpha. Right? Yes, then, do you realize that there is a vector z2 minus z0 which I want to obtain from z1 minus z0. First of all, there are two things. Let's say this is mod of z1 minus z0 is r1, which is the length of this vector, and mod of z2 minus z0 is r2, which is the length of this vector, the magnitude of the two vectors, right? Now, in order that you could obtain z2 minus z0 from z1 minus z0, this is a vector. What are the two things that you should do? One, z1 minus z0 is a vector. First thing that you want to do is, you want to multiply it with e power I alpha so that it coincides with this. Yes or no? Right? You want to multiply it with this. So, now, on multiplying z1 minus z0 with e power I alpha, you get this vector, and this vector z1 minus z0 e power I alpha will be aligned with z2 minus z0. If these two vectors are parallel to each other, if z2 minus z0 is parallel to this vector, isn't it? Because on multiplying z1 minus z0 with e power I alpha, the vector becomes parallel to z2 minus z0. Therefore, this vector will become parallel to this vector. Yes or no? Yes, Therefore, if two vectors are parallel to each other, one can be written as a scalar times another vector. A scalar, in this case, a scalar is a real number. A scalar is a real number. Yes or no? Right? So then, z2 minus z0 and this vector, they are parallel to each other. So this could be written as some scalar real number k times this vector. If two vectors z2 minus z0 and z1 minus z0 are parallel to each other, one could be written as a scalar times the other. Yes or no? Right? Which means, so far so good, yes or no? Yes. Right? Which means z2 minus z0 by z1 minus z0 is k e power I alpha. K is a real number. Clear? Now, argument of z2 minus z0 by z1 minus z0. What's the argument of this complex number? Alpha, isn't it? Is alpha? Right? So what is alpha? Alpha is the angle by which this vector is rotated so that it coincides with this vector, so that it becomes parallel to this vector. Alpha is the angle by which z1 minus z0, that is the denominator vector, be rotated so that it coincides with the numerator. It will not coincide, it will become parallel to the numerator vector. So if someone brings about this expression, then the way to answer this expression is z1 minus z0 is a vector, the denominator vector. I'll call it the denominator. Look, I didn't have the luxury of calling a denominator vector and numerator vector when I had I cap and j cap. But how loosely, frivolously and freely I'm using a denominator vector and numerator vector. I'm dividing by a vector, I'm multiplying by a vector, I'm raising it to a power. All operations performed uninhibited. Yes or no? Yes. Right? That's the prowess. This expression is read as the amount by which the denominator vector be rotated so that it becomes parallel to the numerator vector alpha. The meaning of this expression is the amount by which, you just note down because you would have to read it one more time. The way to read the left hand side is the amount by which the denominator vector be rotated, so that it becomes aligned, with the numerator vector, right? Got me? Now, if you've learned this rotation principle, have you actually registered this rotation principle? Huh? Properly? Huh? Then you've actually come into the thick of things in complex numbers, from where we can go on and on and on and on, right? I'll continue to teach complex numbers till the time that I'm sure the outside noise has vanished. There is a election campaign going on outside, so once I'm sure that they are off, then I'll move to ellipse. Until then, let me keep teaching complex numbers. Is that okay? Okay. Now, so e power I alpha looked upon as an operator which rotates a complex number vector by an angle alpha. If alpha is positive, it rotates it anti-clockwise. If alpha is negative, it rotates it clockwise, right? Now, I is what? I told you it's e power I pi by 2. It's e power I pi by 2. So what would I do? If you multiply a complex number with I, it will rotate the vector by pi by 2, isn't it? Which is not too difficult to see. There is a complex number 30 here. Multiply this complex number is 3 plus I into 0. And if you multiply it with I, this will become 3I. This vector is 3 plus 0I. But where is 3I? This vector is 3I, isn't it? 3I is located here. So do you see that it rotates it by 90 degrees? It rotates it by 90 degrees. So I is an operator which will rotate it by 90 degrees anti-clockwise. Minus I is an operator which is e power minus I pi by 2 which will rotate it by 90 degrees clockwise. 90 degrees clockwise. Minus 1 is e power I pi. So if you multiply a complex number with minus 1, it will rotate the complex number of the vector by 180 degrees anti-clockwise. 180 degrees anti-clockwise. Right? Suppose there is a point A, say Z1, point B, Z2, C, Z3. And say this angle is pi by 4 from this to this anti-clockwise. So then the way to represent this angle is, what is rotated? The denominator vector. In this case, if you want to go pi by 4 anti-clockwise, this must be the denominator vector because the denominator vector is rotated so that it coincides with the numerator vector. The way to read this is Z2 minus Z1 to be rotated so that it coincides with Z3 minus Z1. This vector is Z2 minus Z1. This vector is Z3 minus Z1. Yes or no? And the argument of this means the amount by which the denominator vector be rotated, which is this vector, so that it coincides with the numerator vector, that makes it pi by 4. That makes it, this will be pi by 4. Suppose there is a triangle formed out of 3 points A, B and C whose position vectors are Z1, Z2 and Z3. 3 points with position vectors Z1, Z2 and Z3. Okay. Another triangle A prime, Z1 prime, B prime, Z2 prime, C prime, Z3 prime. Another triangle with vertices having position vectors Z1 prime, Z2 prime and Z3 prime. Suppose this angle is the same as this angle. Suppose this angle is alpha and this is also alpha. How do we represent this? That this angle is equal to this angle. Now, how would this angle be obtained? What is this vector? This vector is Z2 minus Z1. What is this vector? Z3 minus Z1. Now, what is alpha? Alpha is the angle by which the denominator vector, which is this vector, be rotated so that it coincides with the numerator vector, which is this. That means alpha is actually the argument. Now the denominator vector is the one which is rotated, so that's Z2 minus Z1. In order that it becomes aligned with the numerator vector, which is Z3 minus Z1. Then it will be minus alpha. Because see, this is anti-clockwise rotation, so alpha. If I said, what if this is rotated so that it coincides with this, then this will be alpha in the clockwise sense and that will be minus alpha. Right? Now what about this? What is this vector? Z2 prime minus Z1 prime. What is this vector? Z3 prime minus Z1 prime. Now to get alpha, the amount by which you must rotate the denominator vector so that it coincides with the numerator vector. So that's going to be argument of denominator vector is Z2 prime minus Z1 prime divided by Z3 prime minus Z1 prime. Yes or no? Right? And if these two angles are equal, then this will be equal to this. Right? That means argument of Z3 minus Z1 divided by Z2 minus Z1 must be the same as argument of Z3 prime minus Z1 prime divided by Z2 prime minus Z1 prime. Yes or no? Right? Now, suppose these two triangles are similar triangles. Suppose these two triangles are similar triangles. Suppose triangle ABC is similar to triangle A prime, B prime, C prime. ABC is similar to triangle A prime, B prime, C prime. Then SAS condition for similarity. This side proportional to this side proportional to this side, with the included angle being equal, will cause the two triangles to be similar. Yes or no?
Yes, sir.
Right, sir. So, for the two triangles to be similar, what is AB? What represents the length AB? Mod Z2 minus Z1. This is a vector Z2 minus Z1, but mod Z2 minus Z1 represents the length AB. What represents the length AC? Mod Z3 minus Z1. What represents the length A prime, B prime? Mod of this. This mod of Z3 prime minus Z1 prime, right? So, can I say AB by AC? See, with this included angle equal alpha, now AB by AC must be the same as A prime, B prime by A prime, C prime. If these two conditions are met, then the two triangles will be rendered similar. Yes or no? AB by AC means or reverse, AC by AB is the same as A prime C prime by A prime B prime. I can say that also, right? So AC by AB is like a mod of Z3 minus Z1 divided by mod of Z2 minus Z1 equals A prime C prime, which is mod of Z3 prime minus Z1 prime divided by mod of Z2 prime minus Z1 prime. Yes or no? Yes. Right? So far so good? Mod London by mod Patna is mod of London by Patna. Yes or no? Mod London by mod Patna would be mod of London by Patna. Mod Z1 by mod Z2 is mod of Z1 by Z2. Right? So what I do is, can I do this? Same thing I can do on the right hand side. Clear? Now we have two complex numbers. Look, Z3 minus Z1 by Z2 minus Z1 is one complex number, and another complex number is Z3 prime minus Z1 prime divided by Z2 prime minus Z1 prime. These are two complex numbers. Their arguments are the same. Their modulus is the same. Therefore, the two must be identical. The two complex numbers must be the same. The modulus of this is the same as modulus of this complex number. The argument of this complex number is the same as argument of this complex number, which would mean that the two complex numbers must be equal. That means, can I say that this must be equal to this? Can that be said? शशि नहीं. If two complex numbers, यहां से कहां से नहीं समझ में आया, वहां से बताओ. यहां से ये मॉड्यूलस नहीं समझ में आया था. सुनो, ये दो, these are two complex numbers, their arguments are the same, their modulus are the same, therefore the two complex numbers must be the same. This is a complex number, this ratio is a complex number London, this is Patna, modulus London is modulus Patna, argument London is argument Patna, so London equal to Patna, so London equal to Patna, right? If this happens, then these two triangles will be deemed similar. The two triangles will be similar triangles. That means if you cross multiply, then you end up getting would be the condition that these two triangles are similar. Two triangles whose vertices are z1, z2, z3, position vectors, and z1 prime, z2 prime, z3 prime, for them to be similar, this must be the condition. This must be the condition for the two triangles to be similar. Yes, absolutely. If the arguments are the same, then they are in the same direction. So one is scalar times the other. In this case, a scalar would mean a real number, right? Absolutely. Huh? Yes. Z1, Z2, Z3, Z1 prime, Z2 prime, Z3 prime, 1, 1, 1. Suppose this is a line AB. This is Z of A. This is B, which is Z of B. Hello, hello, hello. And say this is C and this is D. I do not know their relative orientations, but all that I know is AB perpendicular to CD. All that I know is AB perpendicular to CD. D could have been here and C could have been here. Or A could have been there and B could have been there. All that I know is that AB perpendicular to CD. And the position vectors of AB, CD are ZA, ZB, ZC, Z3, etc. Right? Now, let's say I take ZB minus ZA and I take ZC minus ZD. Now the amount by which the denominator vector be rotated so that it coincides with the numerator vector is either plus pi by 2 or minus pi by 2 depending on their relative orientations. That means the argument of this would be either plus pi by 2 or minus pi by 2. Would either be plus pi by 2 or minus pi by 2 if they are perpendicular lines. Now if the argument of a complex number is plus minus pi by 2, the complex number must be purely imaginary. Yes or no? So this would mean that ZC minus ZD divided by ZB minus ZA must be purely imaginary. Isn't it? Hey, one thing. If Z is purely real, then z will be the same as z bar. Do you realize this? If z is purely imaginary, right, then z would be minus z bar. Z would be minus z bar. Always. Do you see sense? Z is purely real means z is x plus I into 0. So z bar would also be x minus I into 0, which is the same as x. But if z is say iy, which is purely imaginary, then z bar would be minus iy, and which would be minus z, which would be minus z. Right? ZB minus A. This is ZB minus ZA. Clear? Suppose this is A, ZA, B with position vector ZB, C with position vector ZC, D with position vector ZD. And suppose AB parallel to CD. Suppose AB parallel to CD this time. Right? That means the amount by which, let's say, a vector ZD minus ZC be rotated so that it coincides with ZB minus ZA would either be 0 or pi depending on the orientation, would either be, that means the argument of this would either be 0 or pi depending on their relative orientation. And if the argument of a complex number is 0 or pi, it must be purely real. It must be purely real. And if it's purely real, this must be equal to its conjugate. This must be equal to its conjugate. Right? So far so good. Now suppose there are 4 points, A which is say Z1, B which is Z2, C which is Z3, and D which is Z4. Say in this order. And I want to check if these 4 points are concyclic or not. I want to check if these points are concyclic or not. That means lie on the same circle. Now, if they lie on the same circle, this angle alpha must be equal to this angle alpha. Angles in the same segment. Angles in the same segment. For ABCD to be concyclic, what's required is this angle must be the same as this angle. Hey, how do you obtain this angle? What is this vector? This vector is Z4 minus Z1. What is this vector? Z3 minus Z1. How do you obtain this angle alpha? When you rotate this vector so that it gets aligned with this vector, then you obtain the angle alpha, right? The angle alpha obtained from this would be argument. What is rotated is the denominator vector, which is Z4 minus Z1, in order that it coincides with the numerator vector, which is Z3 minus Z1. Yes or no? And that must be equal to the angle alpha obtained from this. And what is this? Z4 minus Z2. This is Z4 minus Z2. What is this? Z3 minus Z2. So now this vector is rotated counterclockwise by an angle alpha so that it coincides with the numerator vector, which is Z3 minus z2. So this must be the same as argument. The denominator vector is the one which is rotated, z4 minus z2, so that it coincides with the numerator vector which is z3 minus z2. If this happens, z3 minus z2. If this happens, then the points would be deemed concyclic. Right? Hey, but if argument A is argument B, then argument A minus B must be 0. That means if this equals this, that means this minus this must be 0. Right? But argument A minus argument B is argument of A by B. Argument of A by B. Must be 0. If the argument of a complex number is 0, it must be purely real. It must be purely real. That means z3 minus z1 into z3 minus z2 z4 minus z2. Right. Right? Clear? This must be purely real. So if this happens, then ABCD would be concyclic points. Then ABCD would be concyclic points. Yes or no? Can I wipe this off? Now, equation of a circle in complex plane. A circle essentially would have a center, would have a radius, right? Let's say has a center C whose position vector is z0, has a center C whose position vector is z0, right? Has a radius r, and if P be any point, any moving point on this circle, Z is the position vector of any moving point on this circle, right? Then distance between Z and Z0 for any Z on the circle will be r. The radius of the circle r is a real number, right? But what's the distance between P and C? Mod of Z minus Z0. That must necessarily be equal to r. What? Nahin? What is mod Z minus Z0? Distance between Z and Z0. And that must be equal to R for any Z on the circle. So this must be the equation of a circle in the complex plane. A circle with center Z0 and radius R. Equation of a circle with center Z0 and radius R. This is what it is. Yes or no? Right? Since it's too simple for you to assimilate, let me complicate this a little bit so that you feel, oh, you're going into a different plane. All right. Shall I do that? Complicate a little bit the equation of the circle? Huh? I will not do that x plus iy etc. anymore. That's child's play. Your dumb teachers in school did that, convert everything x plus iy, x minus iy. Damn. We'll not do that. We'll have by and large a very mature treatment to the subject. But if you are feeling a little saturated, I move to ellipse now. Are you saturated? Huh? Then okay, might as well, since कर दे, पूरा कर दे. हाँ? अरे बैठ जाओ, बैठ जाओ. जितना तुम लोग ले सको, बाद में जब परेशान हो जाओगे छोड़ देंगे. ठीक है? You have an exam tomorrow? So many of you are in unison. Huh? Huh? I can't. This is getting confusing. I'll stop here. No, don't worry. If this is getting confusing, we'll stop. We'll move to ellipse. We'll start with this anytime you want. Huh? Okay. Let me at least do this. Equation of the I used a wrong word. Complicated. I'm just going to elaborate it. I messed it up for myself by using a wrong jargon, but you felt so threatened when I used that word. Mod z minus z naught equal to r. Right? That's a simple representation of point z whose distance from z naught is a constant representing a circle with center z naught and radius r. R is a real number. Z is any point on a circle centered at z naught. Right? This square would be r squared. Yes or no? Now, see, z suppose is x plus iy, then z bar is x minus iy, and a fact that we learned, z bar, do you realize, is mod z squared? Right? One more thing you would want to check for yourself. If z1 and z2 are two complex numbers, and if I take the bar of this, you will be able to see that it's going to be z1 bar plus z2 bar. If I take the product of two complex numbers and I take the bar of that, then that's going to be z1 bar into z2 bar. You might want to check all of this yourself. If I have two complex numbers z1 and z2, and I took the bar of this, bar of the ratio would be ratio of the bars. Right? These are some properties of conjugates. You'll be able to prove it all by yourself, right? Now, this is mod of a complex number squared. See, mod of London squared is London into London bar, right? So this is going to be z minus z naught into z bar minus z naught bar. That's equal to r squared. Yes or no? Now, this is like z bar, z into z bar, right? Minus z naught bar z minus z naught z bar plus z naught into z naught bar is mod z naught squared minus r squared is 0. Clear? Just multiplying the whole thing. Huh? No, I'll leave it like this. That's okay if you allow me to. Now, suppose minus z naught is a complex number a. Suppose minus z naught is a complex number a. Right? Now if I take, now the bar of minus 1 will be minus 1 only, because minus 1 is a real number. Right? Now if I took the bar of the whole thing, then minus z naught bar. See, I took the bar of the whole thing. Then bar of minus 1 into bar of z naught. But bar of minus 1 will be minus 1 only. So minus 1 into z naught bar, that's a bar. Can that be said? ZZ bar. This then becomes a bar. Minus z naught bar becomes a bar. A bar z minus z naught is a. By our very choice, it's a. A z bar plus. Now, if minus z naught is chosen as a, then mod of minus z naught, which is the same as mod of z naught, right? Because mod of minus 1 will be plus 1. That will be the same as mod of a. A is a complex number. R is a real number. Yes or no? What? So this mod z naught squared would be the same as mod a squared? So this is like mod a squared minus r squared is 0. Right? Now, a is a complex number, but mod a will always be a real number. Mod of a complex number will always be real. So mod a will be real, r will be real. So mod a squared minus r squared will be a real number, right? So this can be written as zz bar plus a bar z plus az bar plus b equal to 0, where b, the real number b, is such that b would be mod a squared minus r squared. And the radius r of the circle is going to be root mod a squared minus b, would be the radius of the circle. Right? So this then is a formal equation of a circle whose center z naught, see, we chose z naught as minus a. Z naught, if a is known, then the center of the circle would be minus a, right? Because we chose minus z naught as a, so z naught would be minus a. And what is a? A is the coefficient of z bar. So minus a will be the center of the circle. The radius of the circle would be root mod a squared minus b, where b is a real number. Now for this to actually represent a circle, b cannot exceed mod a squared. B must be less than or equal to mod a squared. B must be less than or equal to mod a squared. And when b is equal to mod a squared, it becomes a point circle with 0 radius. So zz bar plus a bar z plus az bar plus b, where a is a complex number in general and b is a real number for sure, will represent a circle provided b does not exceed mod a squared. B does not exceed mod a squared. That's okay. No. This is for any z. This is a variable. Different z's will have different values of this. This is a constant. Yes or no? I hope all of you understand this. Mod a squared minus r squared was just taken as b. R would be square root of this. Right?